All right, everybody. Thanks for being here. I know we're getting towards the end of the conference, but hopefully everybody's had lunch and has more energy. So this is Trojan Model Hubs, hacking the ML supply chain and defending yourself from threats. I'm Sam Washko.
And my name is Will Armiros.
And we're senior software engineers at Protect AI. So for an agenda, we're going to go over the idea of public model registries for machine learning models, talk about the risk of model serialization attacks, and how you can mitigate with the open source project ModelScan. Then we're going to talk about private model registries and the idea of zero trust architecture there, and how to apply that to machine learning. And then we're going to talk about using SigStore in conjunction with private model registries. And then maybe have some time for questions. So y'all know about Hugging Face? Sorry, not that Hugging Face. The Hugging Face that's relevant today is the public model hub Hugging Face. Because if you've been around the machine learning ecosystem over the past couple of years, you'll know that there's been a bit of a shift where AI is increasingly democratized. It's no longer just tech giants developing entirely from scratch. A lot of it is now an ecosystem where AI teams rely on these public foundation models where one organization will train a large, more generalized model and on a generalized data set. A lot of times these take a lot of time and resources to train, and they upload that to a model hub like Hugging Face. And then another organization takes that and fine-tunes it to their more specific data, and that's what ends up going into deployment, or sometimes it's an iteration of a couple of fine-tuning rounds. So it increasingly means that machine learning models are part of the supply chain. It's something that's coming into the organization. And there's a very open nature, a community attitude around these model hubs. Everyone's developing on the same models and making them better. And this leads to an attitude of implicit trust, often, in the models from these communities, which leads us open to attacks like model serialization attacks. And in order to save a model, exchange it, move it from one place to another, you need to serialize it. So it's converting that from the artifact into a character stream. It's going to include the tensors, so the large arrays of the weights of each layer, and the model architecture code, so instructions on how to put it back together. And so the serialized format needs all of the information to reconstruct the model, and most of the time that's going to mean it executes code. And in a model serialization attack, an attacker can inject malicious code into the code that needs to execute to unpack the artifact, and that malicious code will then execute automatically during deserialization. So the insidious part of this is that it might not affect the model performance or output or anything, so the user might not know that an attack has been happening right under their nose. This is a visualization of the serialization and deserialization process, going from the model, the byte stream, up to an artifact store that could be Hugging Face, back into the byte stream and model. And during a model serialization attack, injected code is added to the byte stream, either before it hits the artifact store, or if the artifact store itself is something that can be compromised. And then that means we end up with arbitrary code execution during the deserialization process. And this really has become kind of the modern version of the Trojan horse attacks, where we remember from the early internet days where you download a program and it's supposed to do one thing, ends up executing other things on your machine. And it's the same type of idea where your model could run as usual, but ends up with arbitrary code execution in the background. And this means that the attacker can do things like steal credentials or sensitive data that's on the machine, poison other models or data sets that are there, open a backdoor for them to use later. And classic antivirus software like ClamAV doesn't currently catch these types of attacks because it's in the serialized code. they'd be able to identify it if it was deserialized, but by that point, you're already vulnerable to the attack. So it needs a specific tool to detect it, and the pickle format is especially vulnerable to this. Pickle is the Python native format, and it's been known that pickles are unsafe for a long time now. But a lot of these machine learning frameworks still use pickle for deserialization under the hood. Fickling is a pretty famous library now that Trail of Bits released that demonstrated model serialization attack on pickles, but it's notable that other formats, such as Keras, are also vulnerable to this. Keras has a Lambda layer that you can put any arbitrary code in. TensorFlow has some custom operators that can be used for arbitrary code execution, so it's not just Pickle that's vulnerable to this. And it's not solely a theoretical attack. We've scanned a bunch of models on Hugging Face and found over 3,000 publicly available there that would execute arbitrary code on deserialization. And 41% of these were not flagged in any way by Hugging Face. They do have some protections using Pickle Scan, which is a basic serialization attack detector for Pickle, and they use ClamAV. But this misses a lot of ones that are potentially dangerous. So it's just very easy to share these compromised models on the hub due to the community nature that we talked about earlier. Malicious actors can name squat, they can ride on publicity of big popular models. There's, we saw one example of one name squatting 23andMe where it looked really legitimate from the just basic overview, but it was executing arbitrary code. And yeah, it's easy to just claim an incremental improvement on a popular model, like you could download the latest version of llamas and kind of ride the llama. And the community would kind of trust it because it's associated with this big name and download it without thinking about the fact that you could have added an attack. So yeah, it's out of scope for Hugging Face to police this. They say in their documentation explicitly that it's up to the user to determine if something is safe or not. So how do we check for these attacks? Our answer is Model Scan. And this is an open source tool. It's available through pip or cloning on GitHub, and it detects the malicious operators before needing to deserialize and become vulnerable to the attack. So we support all of the Pickle-derived formats, including PyTorch, and some other major model formats that are also vulnerable to this. So this is an overview of the supported formats and what we're doing for each of them. For all of the kind of classic machine learning libraries are serializing in Pickle. And for those, we're going to kind of scan through the opcodes and try to reconstruct what's going to end up executing, looking for operators that are things like exec, eval, runpy, things that touch the OS, like OS and POSIX and things. And then also looking at TensorFlow for read file and write file, and Keras for the Lambda layers. So now, knowing about the existence of this tool, when is it useful to actually use it and scan your models? A couple of different times in the life cycle are useful for it. The first will be anytime you're using a pre-trained model, so probably one of those foundation models from Hugging Face. If you're downloading that and using it in your organization, scan it. Like, you don't want to be introducing something malicious. And then after training and before publishing a model, it's good to have a scan to make sure nothing in that process inserted any vulnerabilities, and you have kind of a last known good record that it was clean before you upload it. Another time that's useful is before our deployment. You don't want to be deploying a model and having it run when it is going to be introducing attacks. So scanning it, like if you're pulling it down from a registry, you don't know if it was tampered with there, scanning it before deployment. So This is just a sample output of, it can be used either as a CLI tool or as Python SDK. The CLI tool by default outputs this console human readable format, going over what issues were found, the severity of them, any specific issues like the severity, description, and source of where it was found. And it's also an option to have it return in JSON for a computer parsable format, or specifying your own custom reporting format, or it's also very modularized to be able to add your own scanners to the workflow, adding middleware. We're trying to make it as configurable and usable as possible. So with that, I will hand it over to Will to talk about the risks with private model registries.
Awesome. Yeah, thanks, Sam. So private model registries, in contrast to the public model hubs that Sam was describing, are not intended for these open-sourced or public-facing models, but instead are for your organization's proprietary models. And these might have been trained on sensitive customer data, or they might just reflect some competitive advantage that you don't want out in the public. And so basically, these private model registries are storing all of your secret sauce AI-type models. So there are several private model registries out there. The most popular open source tool for this is MLflow Registry, which is a fully open source tool that you can deploy within your own organization to store your models. There are a ton of proprietary offerings like weights and biases, offerings from the major cloud providers. And you can also always just forego all these nice registry features and dump your models in S3. But we never see anybody do that ever. So these private model registries are safe, right? We know that access to them is only limited to our internal teams. And we know that hopefully everyone within our organization is being compensated well enough to not be introducing these MSAs ourselves, with the exception of a ByteDance intern from yesterday. That news just came out. And our company has a security team, right? So these should be a safe place to store our models. Well, of course, this would not be a very long portion of the talk if all those were the case. So maybe we can try to challenge some of these assumptions. So in the last year alone, our security research community, Hunter, has found over 20 security vulnerabilities in that open source MLflow registry, all of which were responsibly disclosed and patched before being published. But several of these exploits were critical severity, meaning that they would have allowed for complete system takeover of these MLflow registries. So an attacker could have complete read and write access to all of your proprietary models. And similarly, if you were in that definitely non-existent camp of people who just upload their models to S3, we found that up to 46% of these S3 buckets or other cloud storage buckets that are storing these data science artifacts, like machine learning models, could have misconfigured permissions, which mean that unauthorized people can either read or write to these buckets and potentially tamper with your machine learning models. So this really introduces the need for a zero-trust architecture approach to your private model storage, which basically, as I'm sure many people in the room know, that means zero-trust architecture is the idea of treating even your internal components and processes as if they were untrusted external inputs. And so that way you don't have to implicitly trust any things in your system. And to really hammer home why this is important, we can consider some scary hypotheticals that could happen to a MLOps system. So what would happen if, for instance, a malicious actor gained access to your private model registry, like your MLflow registry, by using one of those exploits? Well, it would be a total free-for-all. Like, they could do whatever they wanted. You wouldn't be able to trust any of those models that you're sitting in storage anymore. So for instance, how would you know that they wouldn't have introduced any new vulnerabilities, like model serialization attacks? Well, this is a bit of a trick question to see if you're paying attention. So for this, you could use model scan, right? And so we do encourage you to use model scan on your private models, just as you would on your public models, because you never know if something might be tampered with. And while you weren't looking, an attacker introduced these attacks, or maybe one of your dependencies introduced the attack. at build time for the model. But lastly, there could be an even more nefarious attack that's done on your models where an attacker could perform what's known as a model poisoning attack. And so what this involves is if you have, for instance, a computer vision model that's trained to identify street signs, for instance, what an attacker could do is they could fine-tune that model with just a few examples of, say, an image of a stop sign with a blue sticker on it. And they could tell your model, for these images of stop signs with a blue sticker on them, actually you should classify them as 80-mile-per-hour speed limit signs instead. And this would be a very, very small tweak to the model. It would only change a few weights, and it wouldn't be a model serialization attack, because it's not executing arbitrary code. It's just making a very, very subtle, certainly undetectable to a human, change to the weights of the model. And of course, you could imagine that if this kind of an attack were to be deployed into, say, a self-driving car, it could be really disastrous if it sees a stop sign with a blue sticker on it in the wild. So how can we know that these models are not just don't have MSAs in them, but haven't been tampered with at all? So this is where we are going to bring in the idea of cryptographic signing and verification, ideally with SigStore, which is an open SSF project. So for those that are unfamiliar, signing and verification is a process that's been around for decades, a very long time, as a way of solving this problem of untrusted artifacts and basically giving you, zero trust confidence that a given artifact that you're using in your software architecture is a trustworthy artifact and is the same one that it sort of claims to be. And we can actually use SigStore, which again is maintained by the OpenSSF community, to implement this signing. And there was a really great talk yesterday that went into a lot of the details of how SigStore works under the hood. I won't get into that on this talk, but just for the sake of a quick overview, we can go through this quick demo. I'm sorry if the text is too small, but I'll sort of explain through what it's doing. But in this demo, we're using SigStore to basically sign and verify, for instance, a model artifact. So here we're requesting that SigStore signs the model artifact that we're passing into it. And it prompts us with this login page where we can just log in with our Google identity. And then SigStore actually uses that to create a signature for the artifact that we passed in. So it not only basically hashes the model artifact to get a snapshot of it at that time, but it also ties that signature to our identity so that only my Google account as a trusted entity, I'm a trusted developer, only I have access to my Google account, only I could create this signature. And so this can't be forged by anyone unless they somehow get access to my Google account. And you would, in production, probably even use a trusted CI account or something like that to provide this identity. And so then later on, when it's time to verify this model artifact, you can pass in your only public information, such as my publicly available email address. And here we can see that SigStore successfully verifies that signature, which is a way of guaranteeing that that model artifact is the exact same one that I had initially passed in. So this is kind of cool to see SigStore doing that in a simple demo format, but that's really not how SigStore might be used in practice. So we want to show how we can use SigStore and this whole zero trust architecture in an end-to-end machine learning model development lifecycle. So to introduce that, we could just quickly review how SigStore is most often used today, which is for signing containers and traditional software artifacts. So if you're building a container, you're going to start by writing some source code. Maybe it's an API server, something like that. And you're going to export that to a container image. And as a good security-minded engineer would, you want to scan that container image with either ClamAV or Trivy to make sure that there are no existing vulnerabilities that were introduced in the build process. Then once you have that degree of confidence that there's nothing nefarious in your container image, you can go through that whole signing process that I just showed, where you use your identity to give your seal of approval on this image, and then you can push it up to a container registry like Docker Hub, and at any point in the future later on, somebody can pull down that image, verify the signature that you attach to it, make sure it's the same exact container image that was pushed up with free vulnerabilities, and then safely deploy your API server or whatever it is into production. So how can we apply this same sort of life cycle that we've been developing throughout like the last several decades of software development experience into the world of machine learning models? So we can go step by step here, but we can see it's actually a pretty similar process that we can start applying. So you're going to start, instead of by writing source code, you're going to start by training a new machine learning model or fine-tuning a foundational model. And to do that, you just need a data set, a machine learning model framework, and maybe a Jupyter notebook. And you eventually get a model that you're happy with, that performs well, and you serialize it into a model artifact, into a model file. And then, of course, we want to make sure that that serialized artifact didn't have anything nasty inserted into it during the build time. So we scan it with model scan to get a clean bill of health. And so now we've just trained this model. We've verified that it's free of attacks. So we know that this model is safe. So now we can sign it with our identity to say, we know that this is, in its current state, a safe model to deploy to production. And now it doesn't matter how long it sits up in MLflow. It doesn't matter how many people come into MLflow and hack your servers and try to modify it. Even if they are successfully able to tamper with your model, we always add this verification step before whenever we pull down a model. And that way, the verification step, if there is some tampering, like a model poisoning attack, this verification step will fail because the signature doesn't match the originally uploaded model in its exact state. And of course, if there hasn't been any issues, then the verification step will succeed, and we will be able to deploy this safely into production. So if we covered a lot of grounds here. So the main takeaways here are that model files, they can be vulnerable to these model serialization attacks. And for that reason, we always want to scan our models, whether they're coming from a public source or even internally, using the open source model scan tool. And lastly, we always want to sign and verify our model artifacts using SigStore, ideally, to establish their authenticity to what was originally built. And with these steps, we can stop the MSA Trojan horses at the gates. So yeah, we'd love to take any questions if you have them. Yeah.
One question I have, I'm not an ML expert, so sorry if this is a stupid question. But
Yes.
are these MSAs, are they, shall we say, inherent? Like my understanding is that model scan will detect any MSA. It doesn't actually evaluate to see like what the MSA is doing. It's just like there's an MSA here, and it flags that. Right?
Yes, yeah, the open source is just saying that it's executing some arbitrary code. It's kind of up to you at that point of, is this a model from a trusted source that a lot of these are by design where the Lambda layers in Keras, for example, are a feature of it. So if you want specific instructions to happen when you're deserializing, like that's, sometimes what is necessary, but it's just saying that, hey, something's there, like, do you trust this source? Investigate it further. Yeah.
Yeah, no stupid questions. That was a good question.
So similar question, not in that sense, but we talked about using cosine to sign your own private models. Is there an effort from the Hugging Face community to sign the models, cosine for public models today? Or is that in their path to say for widely adopted models that has some kind of signature so that you know there hasn't been any tampering?
Yeah, that's a great question. So yeah, that's, not something that we're aware of happening on the Hugging Face side. So yeah, that's why for now we recommend that you do, what you can have control over, which is your own private models. But I think that that's definitely would be a great initiative to do that on the public side as well, similar to, how Sigstore is being used for a lot of, software package managers, I think that would be a great, future direction for the public model hubs to go. But yeah, right now there's no plans for that.
And then if I tie into that, like if I was using model scan to scan a model that was signed by cosign, would it be able to detect that and provide you with a signature or anything around that? Or?
Yeah, so.
Right now, model scan doesn't do anything to integrate with signatures. They're just two separate tools.
But yeah, one thing that we have seen people do is you could actually, have the model scan output as, a JSON file, and then you could actually sign the model file and the model scan output together. And in that sense, you can, basically confirm that, this model scan output, which says there's no vulnerabilities, ties to this model file at verification time. And so that's like another added layer of security. Like how would they be able to like inject that data, kind of? Yeah. So like you could do it. So like Sam mentioned, like there's this idea of fine-tuning models where you take some base model and then you train it with some additional data points. For instance, if you have a general purpose model but you want it to be really good at financial analysis, you can give it some financial data to train it. So you can do that same thing but for malicious purposes, where you train the model to perform some malicious action in some certain edge case, some certain input that it receives. And so it's the same process as this, normal fine-tuning process, but with obviously more malicious.
How do people inject that into your model?
Oh, yeah, so for that, of course, you would need access, like, for instance, to be able to write to the model registry. So they would need to infiltrate it in some way, like either by exploiting some misconfiguration or something like that. So yeah, they would need to write to it.
Anything else?
Any other questions? All right. Okay, thank you so much,
Thank you,
everyone.
everybody.